Hello, we're Team Byte. The project we worked on was Category A on household hydroelectrics from gutters to gigavolts. Our team members are Shash, Perry, Cameron, Esther, Pratika, Cindy, Adam, and Dylan.
This is a gutter system. A traditional gutter system collects water from the top of houses and it follows a path down to some sort of end spout. Some people have it come directly out of this end. Some people have it go into a channel like this tube. Others have it collect in rain barrels. Regardless of what happens, everybody has a place for the water to go once it's come out of the gutter system. Nobody cares what happens to the water while it's still in the gutter system. Gutter system means that the water falls from the roof to the floor. This means that there's a lot of energy that the water produces and is wasted. To utilize that energy, our team has developed a hydroelectric power plant that can work by inserting it into the gutter system. It is a small water wheel that is attached to a motor that is attached to a battery. Though it will not produce the same amount of power that a large-scale hydroelectric power plant may produce by using the ocean or a river, it is undeniable that installing a hydroelectric power plant in the gutter system will get you energy that you were not otherwise getting.
So this is the new design for the gutter. One of the primary differences is that instead of just a 90-degree angle, it goes at a much larger angle, and that is to prevent water from cooling and preventing the rotor from spinning. So the water comes down, spins the rotor, and comes out the bottom. And if you want, you might just attach a hose onto the end, which is something that also you can do on the previous design because the profile for the out is much larger, but now that it's smaller, it doesn't really decrease water flow, and you can attach a hose on the end if you want. So those are some of the design changes, and yeah, that's it.
Here we have a demonstration of the water wheel, using running water from a faucet to replicate the flow of water in a gutter system. Originally prototyped using plastic and spoons, we decided that we required a sturdier wheel and decided to design and create a wheel out of wood. Along with the housing designed by the project design sub-team, the wheel is able to efficiently integrate into a household gutter system. The wheel is small, light, and easy to make, and will be a good addition to many homes. As you can see, it has a relatively decent rotational velocity and kinetic energy, which will later be converted into storable electric energy.
Hello, I am Cindy. I am in the conversion to usable energy team with Pratika. Our objective is to show that the rotational motion can be converted and stored as the usable energy. Me and Pratika split this task into two subtasks. I am responsible for lighting LED with an AC motor. Right now you can see the motor is connected with the LED. So when I manually rotate the motor, it would generate power to light up the LED. So here. So you can see the LED is lighting up by the motor. For the final product, we would design the rotor to generate electricity in a similar way. Thank you.
So since we've shown that we can turn our rotational motion into current, the purpose of this part of the project is to show that we can charge a battery using that current. So for this task, I've constructed a circuit to charge a battery, and I've hooked it up to the Arduino so that we can control and monitor the current going through the circuit. So it'll be powered using a USB port. The power goes into our breadboard and through our battery, and then into a resistor. This one is a 330 ohm resistor. And we have two probes that will measure the voltage before and after the resistor, and we can use that difference and the known resistance to calculate the current through the resistor, which will also be the current through our battery. We also have a MOSFET transistor, which will be used to control the current. And then we go to a capacitor and resistor, which will be used to smooth the PWM signal, and then eventually back down to ground. So here's the code for our circuit. We start by defining some important characteristics of our battery, including the capacity, the max voltage, and then also the resistance of our first resistor. Then we define our analog pins for both of our voltage probes, and also the output pin for our PWM signal. Then I've also defined some variables that will be calculated later, and also our target current, which I've set to be 1/13 of our battery capacity. So when we start, we're going to write the output PWM signal and then read the values at both of our probes and calculate the voltage at those 2 points. We'll use the difference in voltage and the known resistance to calculate the current through our battery, and then we'll print the target current and battery current to our serial monitor. Also going to calculate the battery voltage and print that to our serial monitor, and say that if that value ever exceeds our max voltage, we'll set our PWM signal to 0 and stop the charging and print a message letting us know what happened. So I ran this code, and here's an example of one of the results. Our target current was 250 milliamps, our battery current was 11.24 milliamps, and then our battery voltage was 1300.1 millivolts. So I think one main reason why we weren't able to reach the target current was because of the high resistance value of our first resistor at 330 ohms, which would lead to a higher voltage drop across our battery as opposed to the resistor. I also had problems with the battery voltage exceeding the max voltage, which would also be because of the resistor. So ideally in our final product, we would have a resistor with a low resistance value, maybe around 10 ohms, but it showed that we can charge a battery with some given current and a similar circuit setup.
For calculation, we are using this formula to find the power output from the amount of rainfall. This formula is derived from the potential energy mgh and the law of conservation of energy. What we need are the density of water, the acceleration due to gravity, and the height. This will be the distance from the rooftop to the water wheel, and the volumetric flow rate. Here we came up with a hypothetical condition. Suppose we have a 30 feet by 30 feet rooftop and the height is 6 feet. And suppose we have a heavy rain. For this calculation, it will be 0.3 inches per hour. We have the density of water, the acceleration due to gravity, and the height. We need to find out the volumetric flow rate. First, we want to get the area of rooftop. We find the area and we convert it into inches square, and we get 129,600 inches square. We multiply the area with the rate of rainfall and make conversion. We get 168.3 gallons per hour. This is the volumetric flow rate. For calculation, we convert everything into a metric system. 168.3 gallons per hour is converted into 0.18 liters per second, and the height is equals to 1.8 meters. The density is 0.997 kilograms per liter, and the gravity is 9.8 meters per second square. After plugging these numbers into the formula, we get 3.17 watt. This is a visual we made. The horizontal axis is the rainfall in inches per hour, and the vertical axis is the power output in watts.
From our calculations with the water wheel, we have determined that the general output would be 3.17 watts of power. To turn that into how much electrical energy would be produced, we use the constants for charging an iPhone 6. The rated iPhone 6s battery capacity is 1,715 milliamp hours and is rated to charge at 5 volts. Using this voltage, we use the voltage equation P equals IV, power equals current times voltage. We isolate for I, and we end up finding that I is equal to 6.634 amps, or 634 milliamps. That is the amount of current that the water wheel system produces. To determine how long it would take to charge the phone, we simply divide milliamp hours, shown here, and the milliamps, shown here, which gives us about 2.7 hours. So it would take roughly 2 hours and 42 minutes to fully charge an iPhone 6s with this battery charger system. This energy is good, but it could most definitely be better. To better increase the energy generated from the rain, or to better increase the efficiency of our water wheel, we would take some of the steps below, like having a higher roof to increase the potential energy as the water falls from the roof to the bottom of the gutter system where our water wheel would be located. Or if we have a larger roof to capture more water, that means that there will be more water flowing into the gutters and our flow rate will increase. Some of the energy was lost due to the friction of the water wheel system. If we used a material that decreased the friction significantly, we would see a noticeable increase in the energy output. It is also possible that our wheel design could see some noticeable improvements, whether we change the shape of the wheel to better conform to the water input, or we add more blades. Adding more blades would theoretically cause would cause the wheel to capture more water energy, therefore causing it to spin faster, therefore producing more energy.